Hello, my name is Betsy Barber, and I am talking about projecting population shifts for European diadromous fish species based on climate change scenarios and dispersal dynamics. This project is part of Work Package 5, and the objective is to develop hybrid species distribution models for 11 European diadromous species in order to explore possible distribution changes. And when I say hybrid, I mean that we're combining two modeling approaches, and not that we're looking at the hybridization of species. If we look at the linkages between work packages, we can see that biological data is being provided to the ecological model in Work Package 5 from Work Package 6. And then this is used with other inputs to calculate fish abundance in case study catchments, which are being used as some of the inputs for the economic models in Work Package 4. The ecological models are also being used as inputs for the interactive web atlas in Work Package 7. The first task for Work Package 5 was to update the EuroDiad database to version 4.0. EuroDiad consists of presence-absence and functionality data for diadromous species populations. It includes 350 catchments and 3 time periods. It was validated twice, in 2006 and again as part of the DiadES project, by 49 experts. And it's available as a PostgreSQL database. The next task for Work Package 5 was to develop a framework for hybrid species distribution models. This involved defining equations that combined habitat suitability, population dynamics, and dispersal, and involved estimating unknown parameters using a survey of diadromous species experts who were both within and outside of the DiadES group. For the next few slides, I'll be focusing in on how we defined dispersal, because this is the novel component of this framework. Dispersal consists of 3 components. The first is estimating the proportion of spawners that attempt to disperse to a new catchment. In our example, we have a total number of spawners that are divided into the proportion that spawn in the catchment where they originated, and the proportion that are emigrants that disperse to a new catchment to spawn. And so for dispersal, we're focusing in on this second group. The second component of dispersal was estimating how far these fish can travel. We addressed this using 2 of the questions from the diadromous fish survey. The first asked what is the mean distance that an emigrant is likely to disperse, and the second asked by what distance have the majority of emigrants found a destination catchment, or in other words, at what distance have emigrants stopped dispersing. And we used the answers from these 2 questions to estimate dispersal curves. So in the example on this slide, the different colored lines could represent the dispersal curves for different species, and so you can see there's a range of possibilities. And these are for anadromous species, but we also modified the questions in the survey for catadromous species as well. So we can see these dispersal curves in action using an example. So here's the curve for Alice shad. And we can see that the slope of this curve is actually kind of steep. So this means that most of the fish are moving a relatively short distance, so less than 100 kilometers. But we do still see some fish that are moving a longer distance. And so we use this curve to calculate where fish are moving from a particular catchment. And we're doing this for all of the catchments that are included in the model. Now we can focus in on one particular catchment for our example. So here we are using the Adour as an example, as indicated by the arrow. And we are, say, starting with 10,000 fish that are leaving this river. And then we are asking, where are these fish going? So these circles on the map are representing all of the possible catchments that these fish can disperse to. And the color of the circle represents the number of fish that are dispersing to that catchment. So when you see a yellow color, there's a large number of fish that are dispersing to that catchment. And with the green and the blue, it's a smaller number of fish moving out to the purple dots that only have a few fish that are entering each of those catchments. So we can see for the Adour River that most of the fish are staying relatively close to the catchment, and you only get 1 or 2 fish that are moving into each of these catchments that are further away. The last component is whether or not these fish are surviving. So we apply an additional mortality rate to the fish that are dispersing. So if we go back to our example of Alice shad and we ask how many fish are surviving this dispersal, we can see two main things. The first is if we look at our map, again, the dots are representing the catchments that are receiving fish that are dispersing from the Adour. And we can see that this number of catchments is much smaller than previously. And the second thing that we can see is that the total number of fish is also smaller. So on the previous map, yellow represented about 800 fish, and on this map, yellow represents about 400 fish, and this is because of the additional mortality. Also included in the modeling framework is the option to quantify anthropogenic effects. This includes the effects of habitat degradation, such as pollution, and then also direct mortality, such as a fishery. However, for our preliminary results, we are not including anthropogenic effects, and this is important to keep in mind when interpreting these results. This is because we're still determining how to incorporate catchment-specific information. The next tasks for Work Package 5 then are to run the models and iteratively adjust them as needed, and then compile and disseminate the results. Now I'll be showing some preliminary results from two different species, Alice shad and Thwaite shad. We're presenting our results as a saturation rate. To calculate this, we first need to calculate a maximum value that is set by the habitat suitability. And this is on a gradient between unsuitable habitat and ideal habitat. And this is calculated for each catchment at the time step, so for our example, year. And this represents the maximum capacity, essentially, of the population. And the saturation rate then calculates how close the population is in that catchment in that time period to the maximum or this limit that is set by the value of HSI. Here are the results showing the saturation rate for Thwaite shad for one of the climate models with an RCP scenario of 8.5. The x-axis is showing years from 1951 to 2100. The y-axis is showing individual catchments that are arranged by region and essentially arranged north to south, with north being the top of the figure and south being the bottom. And the colors represent the different values of the saturation rate. So we can look at trends for individual catchments that are represented by rows through time. Now, if you remember for the saturation rate, we have values from 0 to 1. And so when you see a yellow box, essentially, you're seeing that the saturation rate is at 1. And so the population is at its maximum level as set by the habitat suitability in that catchment for that time period. A red color for saturation rate indicates that the value is at about 0.5, and that means that the population is only at about half of its maximum potential. When we see a blue color, that means that the value for saturation rate is relatively small, and means that the population is relatively low compared to its maximum potential. So if we look at this figure, we can see for Thwaite shad that quite a lot of catchments through time are at that higher value, that yellow value, where it has a very high saturation rate. So it's close to the maximum that's set by the habitat suitability. Again, keep in mind that these results do not include anthropogenic effects. So this is just looking at the effect of environmental factors, dispersal, and population growth. We can see a few trends if we look at particular years, where in between particular years, the saturation rate has decreased quite dramatically, so going from a yellow to a blue. And then after that decrease has happened, we do see the population over a certain period of time essentially recovering and going back up to a higher saturation rate. If we compare the results for the two different shad species, so now we've added in the bottom panel the results for Alice shad for the same climate model and the same RCP scenario, we can see that for Alice shad, these trends are quite variable through time. So we see differences between years in a relatively short period of time, and we also see differences between catchments that are relatively close within a region. In summary, we can see from our preliminary results that two shad species that are ecologically similar do have different spatial and temporal trends. For Thwaite shad, we see a general trend of populations that are close to their capacity based on the saturation rate. And this could suggest greater stability through time, which could potentially translate to the development of a fishery. For Alice shad, we see a lot of annual variability in the saturation rate, and this is across the catchments and also through time. And this could suggest more population fluctuation, which could make it more difficult to consistently utilize a resource. So moving forward, we want to add multiple climate scenarios, so adding RCP 4.5, and then also have a time step based on the life history of each of the species. Thank you to everyone for listening, and thank you to all the project partners and people who filled out the survey and helped with the validation.